Hello, everyone. Thank you for joining another EcoRebuild LA mini class. My name is Lucas Ann, and I'm currently a rising 11th grader at South Pasadena High School. Before we start, I want to set the expectations for today's session. This is not going to be a basic introduction to energy. We already covered things like renewable and non-renewable energy, energy efficiency, and smart energy, as well as home clean energy systems in earlier three classes. Instead, today is about something much more forward-looking. We are going to explore the future of energy systems, not just from a technical perspective, but from a broader perspective of how energy might reshape society, cities, economies, and even the long-term direction of civilization. Most people think of energy as something very practical, like electricity bills or fuel in cars. But if you zoom out far enough, energy is actually one of the most fundamental forces shaping human progress. Everything we do depends on it: communication, transportation, healthcare, artificial intelligence, and global trade. There are also long-term visions from innovators like Elon Musk who often talk about how humanity may eventually scale energy systems far beyond Earth. So the real question is not what is energy today, but rather what will energy allow humanity to become in the future? This is what we are going to explore step by step. To understand the future of energy, we first need to understand what is actually changing right now. Energy is not evolving in one single direction. It is going through multiple transformations at the same time, and each of them is equally important. The first shift is the most obvious one: the transition from fossil fuels to clean energy. This includes solar, wind, hydro, and other low carbon energy sources replacing coal, oil, and natural gas. But at the same time, there's a second shift happening that is less visible, but just as important. Energy systems are becoming digital. In the past, electricity grids were mostly physical infrastructure. Power plants generated electricity and it flowed in one direction through transmission lines to homes and businesses. The system was relatively static and predictable. Now that structure is changing. Modern energy systems are becoming highly connected digital networks. They use sensors, real-time data, and software systems to monitor and control electricity flow continuously. The third shift is decentralization. Instead of relying only on large centralized power plants, we now have millions of distributed energy sources. Rooftop solar panels, home batteries, electric vehicles, and even small community microgrids are becoming part of the energy ecosystem. This means energy is no longer controlled by a single source. It becomes a network of interconnected nodes. And finally, artificial intelligence is becoming part of the system. AI is now being used to predict electricity demand, optimize grid performance, and reduce energy waste in real time. When you combine all of these shifts together, energy stops being just a physical system. It becomes something dynamic, adaptive, and intelligent. One of the most important ideas in this entire topic is that energy is not just one industry among many. It is actually the foundation of a civilization itself. If we look at human history, even major transformation is directly tied to energy systems. In early human history, fire was the first major energy breakthrough. It allowed humans to cook food, survive colder climates, and expand into new environments. Later, agriculture created a more stable energy system based on food production. This allowed humans to settle, form communities, and eventually build cities. Then came the Industrial Revolution, powered by coal. This was the first time humans had access to large-scale mechanical energy. It completely changed production, systems, transportation, and urban development. After that, oil and gas became dominant. They enabled global transportation networks, aviation, and international trade, creating the modern global economy we live in today. So, if you step back and look at history as a whole, energy is not just supporting civilization, it is actually what defines what civilization is capable of at any given time. Without energy, nothing functions. With better energy systems, everything expands. For most of human history, energy has been defined by scarcity. We had to extract it from nature, transport it over long distances, and carefully manage how it was consumed. This created a system where energy was always something limited and controlled. But now, we're entering a very different phase. We are moving towards what many people describe as an energy abundance transition. This does not mean energy becomes infinite. Instead, it means energy becomes extremely efficient, widely distributed, and much easier to access. A simple example is solar energy. The sun produces an enormous amount of energy every second. In fact, the Earth receives more energy from the sun in 1 hour than all human activity consumes in an entire year. So the real limitation is not energy itself. The limitation is our ability to capture, store, and distribute it efficiently. This is very similar to what happened with information. In the past, information was scarce. You had to go to libraries or institutions to access knowledge. Now with the internet, information is abundant and instantly available everywhere. Energy is going through a similar transformation, from scarcity-based systems to abundance-based systems driven by technology and optimization. Solar energy is one of the most important foundations of future clean energy systems, not because it is new, but because it is extremely scalable and available everywhere on Earth. In the future, solar energy will not look like what we see today. Right now, solar panels are still visible objects installed on rooftops or in large solar farms. But in the future, solar technology will become fully integrated into the environment. Buildings will have solar materials built into walls, windows, and roofs. Roads may generate electricity through embedded materials. Even vehicles may include solar surfaces to extend their energy range. At that point, energy generation becomes almost invisible. It is no longer a separate system, it becomes part of architecture and design. This is a very important shift because it changes how we think about infrastructure. Instead of building energy facilities, we will design environments where energy is naturally collected everywhere. And if we extend this idea further into the long term, there are even concepts like space-based solar energy collection. In space, solar radiation is constant and not affected by weather or nighttime cycles. This idea is still in early development, but it represents a clear direction. Energy systems are becoming less constrained by geography and more integrated into larger scale environments. Energy storage is one of the most critical components of future energy systems. The reason is simple. Renewable energy is not always available. Solar energy disappears at night. Wind energy fluctuates depending on weather conditions. This creates a natural mismatch between energy production and energy demand. Without storage, renewable energy cannot fully replace traditional energy systems because supply and demand must match in real time. But with storage, this limitation is removed. Energy storage allows us to shift electricity across time. We can generate energy when conditions are ideal and use it later when demand is higher. For example, we can store excess solar energy produced during the daytime and use it at night. We can also balance seasonal variations by storing energy during high production periods and using it later. This is why batteries storage systems are not just supporting technologies. They are core infrastructure systems similar to transportation networks or communication systems. As storage technologies improve, renewable energy becomes more reliable, stable, and scalable. It moves from being a supplementary energy source to becoming a dominant global system. Hydrogen energy is often misunderstood as a direct competitor to electricity, but in reality, it plays a very different role. Hydrogen is not mainly meant to replace batteries or solar power. Instead, it acts as a bridge fuel or a complementary energy carrier, especially in areas where direct electrification is difficult or inefficient. There are several industries where electricity alone is not enough. For example, steel production requires extremely high temperatures. Long-distance shipping and aviation requires fuels with very high energy density. Heavy-duty trucking also requires long-range energy systems that are difficult to fully electrify with current battery technology. Hydrogen becomes important in these sectors because it can store and deliver energy in a different form. When hydrogen is used in fuel cells, it produces electricity, and the only byproduct is water vapor. That makes it very attractive from a clean energy perspective. However, the biggest challenge today is not usage, it is production. Most hydrogen currently produced in the world comes from natural gas, which still generates carbon emissions. This is known as a gray hydrogen. The future goal is a green hydrogen, which is produced using renewable electricity, such as solar and wind power, to split water molecules into hydrogen and oxygen. If this process becomes cheaper and more scalable, hydrogen could become a major solution for decarbonizing heavy industries that are otherwise difficult to electrify. So hydrogen is not the main energy source of the future, but it is a critical supporting layer in a fully decarbonized energy system. Nuclear fusion. Nuclear fusion is one of the most ambitious energy technologies ever explored by humanity. To understand fusion, it helps to think about the sun. The sun does not produce energy through burning fuel. Instead, it produces energy through nuclear fusion, where hydrogen atoms combine under extreme pressure and temperatures to form helium, releasing enormous amounts of energy in the process. Scientists are trying to recreate this process on Earth. If successful, a nuclear fusion could represent a nearly unlimited source of clean energy. The fuel for fusion, such as hydrogen isotopes, is extremely abundant and can be extracted from water. This means the potential energy supply is essentially global and long-term sustainable. Another major advantage is that fusion does not produce long-lived radioactive waste like traditional nuclear fission plants. It also does not produce carbon emissions during operation. However, the challenge is extremely difficult. Fusion requires conditions that are hotter than the core of the sun and must be controlled using advanced magnetic confinement systems or laser-based technologies. Despite decades of research, we are still in the experimental stage. But progress is accelerating, and many scientists believe fusion may become viable in the future, even if it takes decades. If fusion is eventually achieved at scale, it could completely transform global energy systems. It would remove most limitations on energy supply and potentially unlock entirely new levels of technological development. The future of energy is not just about how electricity is produced, it is also about how it is managed. Traditional power grids were designed as one-way systems. Electricity flows from large centralized power plants in homes, businesses, and factories. This system is relatively static and predictable. But future energy systems are becoming much more dynamic and intelligent. Smart grids transform electricity networks into digital systems. They use sensors, communication technologies, and software platforms to continuously monitor energy production and consumption. This allows the system to respond in real time. If energy demand suddenly increases in one area, the grid can automatically adjust supply from other sources. If renewable energy production drops due to energy conditions and due to weather conditions, storage systems or backup sources can compensate. This creates a self-balancing network where energy is constantly optimized rather than manually controlled. In the future, energy infrastructure will function more like the internet. Instead of fixed pathways, energy will flow dynamically through a network depending on demand, availability, and efficiency. This shift is extremely important because it allows renewable energy systems to scale much more effectively. Artificial intelligence is becoming deeply integrated into modern energy systems. One of the most important roles of AI is prediction. Energy systems are highly dependent on demand patterns, which change throughout the day, week, and seasons. AI can analyze historical and real-time data to predict when and where energy will be needed. This allows energy providers to adjust supply in advance, rather than reacting after demand changes occur. Another important role is optimization. AI can manage complex energy flows across large regions, ensuring that electricity is distributed in the most efficient way possible. This reduces waste and improves overall system stability. AI also plays a major role in maintenance and reliability. By monitoring equipment performance, AI systems can detect early signs of failure before they become serious problems. This helps prevent blackouts and reduces infrastructure downtime. In addition, AI can improve energy efficiency in buildings, transportation systems, and industrial processes. It can automatically adjust heating, cooling, lighting, and production schedules to minimize unnecessary energy use. Over time, AI will not just be a tool used in energy systems. It will become a core part of how energy systems operate, acting as an intelligent layer that connects all parts of infrastructure. Transportation is one of the largest consumers of energy in modern society, and it is undergoing a major transformation. The most visible change is a shift from gasoline-powered vehicles to electric vehicles. EVs are more efficient, produce zero tailpipe emissions, and can be powered by renewable energy sources. But the transformation goes beyond personal cars. For long distance and heavy transportation, hydrogen-powered trucks and fuel cell systems are being explored as potential solutions. These systems can provide longer range and faster refueling compared to current battery technology. At the same time, many countries are investing in high-speed rail systems, which provide a more energy-efficient alternative to air travel for medium-distance transportation. Another important development is autonomous transportation. Self-driving systems, combined with electric infrastructure, could significantly improve efficiency by reducing traffic congestion and optimizing travel routes. In the future, transportation will not be an isolated system. It will be directly connected to energy infrastructure. Vehicles may even act as mobile energy storage units, feeding electricity back from the grid when needed. This creates a fully integrated energy transport ecosystem. Buildings are always evolving from passive energy consumers into active energy systems. In the traditional model, buildings consume electricity, heating, and cooling from external sources, and energy flows in one direction. But in the future, buildings will become energy producers as well. Many homes will generate electricity using rooftop solar systems or building integrated solar materials. This allows them to produce part or all of their energy needs. In addition, buildings will increasingly include energy storage systems. This allows homes and offices to store excess energy during the day and use it later when needed. Smart energy management systems will also become common. These systems can automatically adjust lighting, temperature, and appliance usage based on real-time conditions, occupancy, and energy prices. The goal is to move towards net zero or even net positive buildings, which produce as much or more energy than they consume. This shift is important because buildings represent a large portion of global energy consumption. Improving their efficiency has a major impact on overall energy demand. Future cities will be fundamentally different from today's cities because energy systems will be fully integrated into urban design. Instead of treating energy, transportation, and infrastructure as separate systems, future cities will combine them into one interconnected network. Traffic systems will be managed by AI to reduce congestion and optimize flow. Public transportation will become mostly electric, with expanded rail and bus systems powered by clean energy. Buildings will be connected through smart grids that balance energy supply and demand across entire neighborhoods and districts. Urban design will also focus more on sustainability. Cities will include more green spaces, energy efficient buildings, and climate resilient infrastructure designed to handle extreme weather conditions. In this model, cities are no longer just consumers of energy, they become active participants in managing and optimizing energy use. Even though future energy technologies are very promising, there are still significant challenges that need to be solved. The first challenge is cost. Building new energy infrastructure, upgrading power grids, and developing advanced technologies like fusion and large-scale storage requires huge financial investment. The second challenge is technological limitation, especially in energy storage. While progress is being made, current battery technology is still not sufficient for fully stable, long-duration renewable energy systems in all conditions. The third challenge is infrastructure transition. Existing energy systems are deeply embedded in modern society, and replacing them takes time, coordination, and careful planning. The fourth challenge is policy and global coordination. Different countries have different energy resources, economic priorities, and regulatory systems. This makes global energy transition complex and uneven. So while the direction is clear, the transition itself is not simple or fast. It requires cooperation across governments, industries, and communities. Here in California, we can already see many of the elements of the future energy system taking shape. Solar energy is widely adopted across residential and commercial buildings. Many homes now generate a significant portion of their electricity through rooftop solar systems. Electricity vehicle adoption is also rapidly increasing. EVs are becoming a common part of daily transportation, supported by expanding charging infrastructure. California also has some of the most ambitious clean energy policies in the US, encouraging the transition towards renewable energy and electrification. In addition, California benefits from strong natural conditions for solar power, making it one of the most suitable regions for large-scale renewable energy development. So while the global energy transition is still in progress, California is already acting as an early example of what a future energy system might look like. To conclude, the future of energy is not just about replacing fossil fuels with renewable energy sources. It is about a much deeper transformation of civilization itself. We are moving from a world of scarcity to a world of abundance. From physical systems to intelligent digital systems, from centralized infrastructure to distributed networks, and potentially in the very long term, from earth-bound systems to space-scale energy concepts. Energy determines what humanity is capable of achieving. It defines how we live, how we build cities, how we travel, and how far we can expand as a civilization. But the most important thing is this. We are still in the early stages of this transformation. The systems being built today, solar infrastructure, batteries, AI grids, and electric transportation, are the foundations of the next era. And the decisions we make now will shape the world for decades or even generations. So the future of energy is not something far away. It is something that is already being built today. That's it for today's presentation. This was the fourth and final class in our EcoRebuild LA Series 1, Energy and Clean Power. We hope you enjoyed the series and gained valuable insights into clean energy topics. We'll be launching additional mini-class series on other sustainability and resilience topics in the future, so we encourage you to stay connected and join us again. Now, we'd love to hear from you. We'll move into our Q&A session. If you have any questions, please type them in the Zoom chat and we'll discuss them together.